class. I just wanted to go over the notes again for Thursday or Friday, just in case anyone was absent or wanted to see them again on the Nearpod. So this is for either 917 or 918. And so I'm going to get started with the notes, okay? So we're talking about taking the algebra that we'd been going over last week and then combining it now with some geometry terms. And so we're going to be learning a new postulate today. And if you recall, a postulate is basically just a rule that we don't have to prove to be true. So it's a very simple rule, okay? So I'm going to teach you this geometry rule, but then we're going to apply algebra to it. And so it's going to kind of make it a little more complicated. So we're going to do a bunch of examples today so that we can see that. What I wanted to show you first is geometry versus algebra when we're talking about symbols. And so if we're talking about two line segments and we're just talking about them, so we're saying like line segment AB and line segment CD, if they're congruent, it means they're equal, right? But in geometry, we use this symbol congruent on top. And the reason for that is because we don't use the equal sign unless we're talking about the actual measurement. And so if we are talking about the measurement of an angle or the measurement of a segment with actual value, then we would use the equal sign, okay? When we're just talking about the letters or the numbers of the symbols, we use the word congruent, okay? So if I go to the next slide, this is where we're talking about the segment addition postulate, okay? And the segment addition postulate is kind of interesting. It's got a really long word, but it's not that bad, okay? So again, postulate is a rule. And so I want you to think about a piece of raw spaghetti, okay? So pretend we're holding a piece of raw spaghetti. And if I were to break that spaghetti, right, to fit it in the pot or something, I've now got two pieces. Now, we could say that one piece is AB, which is 4 centimeters, if you look at the example. And we can say the other piece is BC, which is 10 centimeters. My original spaghetti then, when it was put together, was how long? Well, it's going to be one piece plus the other piece that makes the whole. And so in this case, we've got 14. So it's saying that our spaghetti was 14 centimeters long, and the way we could figure that out is because I was able to tell you my small piece was 4 centimeters and my large piece was 10. And adding them together, I got 14, okay? And depending on where you break the spaghetti, it could give you different values. But that piece of spaghetti is still 14 centimeters. So even if I broke it a different direction or a different part of the spaghetti, it's still 14 centimeters, but now maybe A, B, and B, C are different measurements. But still, if I add them back together, my entire piece of raw spaghetti is 14 centimeters, okay? And that's how this postulate's gonna work, is we are going to find that the pieces add up to the whole. And this might not look bad right now when we're talking about numbers, because we have 4 and 10, and we can easily add that. But when we start adding some algebra into the mix, it's going to get a little more complicated, okay? What I also want to mention about the segment addition postulate is in order for this to be true, all the points must be collinear, meaning we must be talking about points that exist on a line. And that makes sense because if it's a segment addition postulate, then the points must be on that line, okay? So let's look at an example where maybe we have our spaghetti and we're saying that this spaghetti piece is really long. It's 36 centimeters, okay? And so we've got our AC as our spaghetti, and it's 36. And then we break it. They're then telling us that one of those pieces is 21. Can I find the other piece? And so in this case, I know the total amount, and then I know the length of one piece. So to find the length of the other piece, I'm still going to use this geometric expression up top, the AB plus the BC equals the AC. But now I have the AB and I have the AC, and so I would have to subtract in this case, okay? So we can still use the same postulate. We're just solving for a piece of it rather than the total. Okay. So finding the length of mn is very similar to the one I just went over, but we can also write an algebraic expression. So a geometric expression, right, geometry, is when we're using the letters. So I could say LM plus NM equals LN. That's a geometric statement, okay? If I want to write an algebraic expression, I can replace that mn with an x. And now I can say 15 plus x equals 20. And so I'm still using the segment addition postulate. The two smaller pieces added together makes the whole. But now I've set it up as an algebraic expression. And right now, that kind of seems silly because you're like, well, I can easily do 20 minus 15 in my head and get 5. But when I start adding harder algebraic expressions, this simple process still needs to be used with the tougher questions. So it's good practice to start getting your brain to start saying, okay, 15 plus x equals 20. And that way I know the small plus the small piece equals the large piece all together. And so we can see what happens after that. And so here's an example of it. Okay, so this piece, where my arrow is the geometric statement, the geometry statement. Down here is an algebraic expression because we're talking about the value. All right, let's try one that's a little harder. So in this case, we still have two pieces. We have ds plus st equals dt. The issue is now we don't have numbers for our small pieces. We have algebraic expressions. So we need to put this together, and we need to say 2x minus 8 plus the other small piece, which the other small piece in this case is 3x minus 12. Those two equal the 60. So if you were to write this down right now, you would write 2x minus 8 plus 3x minus 12 equals 60. And then now you can start combining like terms and solving. Okay? So let's look at it. On the right, 2x minus 8 plus 3x minus 12 equals 60. I'm solving, I'm saying this piece plus this piece equals the whole. And right now I'm just solving for x, okay? So if I combine like terms, I've got 2x plus 3x, it gives me the 5x. I've got a negative 8 and a negative 12, that goes to negative 20. That equals 60. And then if I add 20, I get 80 over here. And then 80 divided by 5 is 16. So in this case, x is equal to 16. Now, you got to be careful. Some of the questions on the homework say solve for x. Other questions say solve for a certain segment. In this case, it says solve for ds. So if I go back up here, ds was represented by 2x minus 8. Well, now I know x. So I'm going to put x in as 16. I'm going to substitute 16 in. So now I have 2 times 16 minus 8. Okay, so I get 32 minus 8. And so now I know that ds is 24. So I've now taken the segment addition postulate. I'm still using it. One piece of the spaghetti plus the other piece of the spaghetti makes the whole spaghetti, right? But it's gotten a little more complicated because we added algebra. All right, let's do a couple more. Okay, this one's kind of interesting. Again, we have the segment addition postulate, but how would we set up this one? This one tells me that there's a midpoint. So I'm going to look at example 3 on the bottom. I have the whole spaghetti is AB. It's telling me that C is in the middle. What if I broke my spaghetti perfectly in half? Not very likely. But if I did, then my two pieces would be equal. And that's what example 3 is saying. Example 3 is saying that AC and CB are equal because C is a midpoint. Okay, another word you might see again is bisect or bisector. So if there's a question that talks about bisecting a segment, it's cutting it in half. When that happens, you know that AC is equal to CB, and you can set those two algebraic expressions equal to each other. So in this case, I can say 2x plus 1 equals 3x minus 4. In class, we did kind of our own little bulletin board where we wrote the expression out. I don't think it might let me do it here, okay? And so we were able to say 2x plus 1 is equal to 3x minus 4, okay? So down here, you can see I wrote it in the little chat. Now I can solve. If I start bringing things over, I can say, if I subtract 2x from both sides, I'm going to have 1 equals x minus 4. Then I can bring that 4 over. I'm going to add 4 to both sides. So 5 equals x. Okay? Then I could plug the x back in. So in this case, I asked the class to solve for AC. AC up here is the 2x plus the 1. So down here, I can say 2 times 5, because 5 is x, plus 1 is going to equal 11. And so in this case, down here, I can say that AC is 11. Okay? All right, and then we just played a little game. So we're going to do one more example together. It's kind of hard to see this, so I'm going to read it out loud. So if you want to follow along, you can write this on a piece of paper, or you can pause real quick and grab a piece of paper. But we're going to say solve for x. So in this case, I have a line segment AAB, and then it's cut into two pieces. Again, our spaghetti or a string is cut. And so we say x plus 2 plus the other piece, which is 3x minus 9, equals 6x minus 21. And so on the left-hand side, I can combine like terms. And hopefully you're following along on a piece of paper with this. I can combine the 3x and the x on the left side. That'll give me 4x. On the left side, I can also combine the positive 2 and the negative 9. That gives me a negative 7. And then on the right side, there's nothing to combine, so I'm just going to bring that down. So by just combining, I now have 4x minus 7 equals 6x minus 21. From there, I can now start doing inverse operation and solve for x. So I'm going to subtract 4x from both sides. That leaves me with negative 7 equals 2x minus 21. I'm now going to add that 21 to both sides. On the left side, I now have 21 minus 7. That gives me 14 equals 2x. Divide both sides by 2, and so x is 7. And so if you were playing the game with us in class, you'd see that it's the yellow box is the answer. Okay, so go ahead and go into Google Classroom and open up your classwork, and please get that done, okay? Thank you very much, guys.